y desde hace 12 años más o menos se movió a la Universidad de Pensilvania de vuelta, en donde es jefe del área de estudios. Sí, de la Escuela de Medicina. What else? You just told me on something else, but el programa de graduados de allá, y se ha dedicado también. The dean. And then he has a lot of experience in the protocols, en los protocolos de investigación en animales. Se me cruzan los cables, perdón. Y acerca de primates, o sea, él ha sido director de, establece los protocolos en todo el país, en todo Estados Unidos, entonces sabe mucho de eso, y nos va a hablar hoy del sistema acústico, que para mí es el favorito en cuanto a percepción del cerebro, ¿no? Y Vanik también está aquí con nosotros, que es la nueva investigadora, también sabe mucho del tema, entonces para nosotros es un honor tener a Yale Cohen aquí. Muchas gracias por venir.
Not sure it's connecting. Oh, there it goes. Yeah. Yeah. Yeah, connected. Oh, that seems promising. Don't touch. So thank you, Louise, for your very, very kind introduction, and thank you for your friendship and inviting me here. And it's been a lovely, lovely visit so far, and I appreciate everyone coming. So what I want to do is first, introduce sort of our motivating question. And essentially what our lab is interested at various levels is understanding how you take a mixture of acoustic stimuli that are unlabeled and then turn them into very distinct perceptions that are in our head. So a band is a great example of this, right? There's 4 different musicians, and each of them are creating their own acoustic signal, right? And those acoustic signals get mixed. And let me just for I told Luis about this, but just for a point of edification, this is a very intelligent band. So the fiddle player here, she has her bachelor's degree in English from Princeton University, and the banjo player here has a PhD in biology from MIT. And the day after he defended his thesis, he went on tour with Bruce Springsteen. So he actually made a real career for his life. So, right. And so what happens is right, each of these musicians creates an acoustic signal. And then in our ear, we have this mixture of stimuli, right? But in our head, they're completely distinct stimuli, right? We can hear the banjo, we can hear the singer, and we can even, with relatively little, effort, we can pay attention to the singer and not hear the banjo player, right? So the question is how do you go from this physical stimulus to this perception in our head? So this involves obviously a lot of transformations that occur in the brain. I'm going to present them to you in some sort of order. I don't necessarily think they occur in that order, but just to do it in an order. So obviously, the first thing that has to happen is that acoustic signal needs to be encoded in the brain. So you have to go from some sort of acoustic physical stimulus to some sort of electrical, biochemical type of signal in the brain. The next thing, and we're focusing on this, is that there needs to be some sort of what we call feature grouping and segregation, right? So here is one of these word clouds, right? And so even if you don't know what any of these words mean, you sort of can see that there's, you sort of would group these symbols together because they're about the same size, they're the same color, and they're next to each other. So there's some common features of those symbols that make you think they belong together, right? Even though you may not be able to understand the word, if it's in a language or whatever. And you think that this is one group and segregated from this group. You think that they are different groups because they're physically separated and they're a different size, even though they have the same color, right? And in contrast here, you have something that's in a different color and a different orientation. So what you want to be able to do is take, for here, the segregation and features is like the different stimuli that, say, the banjo player is playing. You want to be able to separate that from the acoustic stimulus, right? But then you have to sort of, and the problem is breaking it down and putting it back together. Another thing you want to do is you want to create what we call perceptual categories. So here is a picture of UNAM, right, at two different scales, right? You can easily understand that it's the same symbol independent of the size, right? And as if I move closer to you or further away, you can still recognize me as the same entity, and if I make my voice softer or louder. So that's a perceptual category where you say that these are the same things, just independent of sort of slight perceptual differences. And then there's more complex things the brain has to do, and we call these sort of abstract categories. And these are categories in which you're taking information about perceptual information and linking it with memory information, right? So what I'm showing you here is these are called spectrograms. So x-axis is time, y-axis is frequency, and the color represents how much energy there is at each time frequency point. And these are monkey rhesus macaque vocalizations. And if you just, and so this is what's called a harmonic arch. Can everyone hear it in the back? We lost the sound. Here, yep, okay. And this is called a warble. So to us, they sound different, right? If you look at them physically, they sound different. But to our monkey friends, they mean the same thing. They're almost synonyms, right? Here is what's called a grunt, and this is a coo. Once again, distinct sounds, distinct physical properties, but yet to our monkey friends, they mean the same thing. And you can show this behaviorally. We've shown this neurally, that the brain, treats these as the same stimulus, right? So these are abstract categories where you combine perceptual information with learned information about the universe, right? So you could think about, like a beanbag chair, right? It looks like a big floppy thing. There's nothing about it that tells you that you should sit in it, but we know that through our learned experiences, we know you can sit in it. So you think about it in the same sort of broad category as, the chairs you're all sitting in now, or the chairs that are up to my left. And then another thing you have to do is you have to do what's called a perceptual decision, in which you have all this information in your brain, and somehow you have to decide that is Yale's voice, that is Louise's voice, that is and so where and how in the brain does it is sort of an important part of this whole concept. So for today, though, we want to focus on feature grouping and segregation. Okay, so there's different ways one can do this. There's different ways the brain does it, using these ideas of looking at features that are common. So what I'm showing you here is an example of what we call spectral integration and also sort of temporal continuity. So we have time on the x-axis and frequency on our y-axis. And what you could see here is that there's 3, 6, 7, 8. There's 8 stimuli that are sort of played together, right? And then 3 of them start moving up and down, right? So this up here, it starts at 3.2 kilohertz. Then all of a sudden it goes up in frequency, down, up, down, up, down. Now these 3 are moving up and down together. So what our brain assumes is things that are changing together belong together, and things that aren't changing don't belong. So you want to do is you want to group the things that move together and segregate them from the things that don't move. And then they come back together and everything is constant again. So when you hear this, and I'll play this, what you should hear is you hear one thing, then you hear 2 things, and then you go back to hearing one thing. Okay? So hopefully this works. You can hear it in the back. All right, play it again. So maybe those in front, you should, hopefully you heard that, you heard this. Hopefully you heard you heard that, once again, these two things. You heard the thing moving up, sound moving up and down across this common background. So that's this idea of spectral integration and temporal integration. You can also do this in another way. So here you can have tone bursts that are going from, say, high frequency to low frequency, back and forth. And then you could also have them going very fast, transitioning very fast. And in this case, what the brain assumes that is things that change slowly, right? I'm walking across the stage slowly, you sort of assume it's the same entity, right? But however, if I'm here and all of a sudden I turned up over there, you might think that I'm a different person or a different thing, because we don't expect quick changes, right? So in the auditory system, when it's slow, you're going to link these different tone bursts together, and you sort of will hear one thing, one sound. But when they're fast, there's a perception of two different things. Let me. This is a little more subtle. Let me see if I can fix the settings. Hopefully that will do it. Okay. So that's the slow. So it's almost like you hear this like second sound sort of coming out, popping out. Okay, I'll play it one more time. So it's sort of like a smooth trajectory, right? You sort of think they're. No, it's like there's two distinct things, something that's sort of popping out in the background. So these phenomena, so those were examples from Al Bregman, and who has, you can download like 40 different examples of these, right? And these people know about these ideas. So Mozart, he didn't know these terms, but music was written in ways where people took advantage of. They didn't have the right, scientific words. But this is well known among all sorts of communities that do music and cultures done music. They're able to take advantage of these things. But, so these are well known, they're well studied psychophysically, but what we really don't know is the neural basis of these, right? So what I want to do today is sort of go through some preliminary data, more published data, to show you sort of how we've begun to think about these different sort of parsing and segregating the auditory scene. And to give you some sort of sense of where we'll be going on, what I'm showing you here is a side view of a rhesus macaque brain. This is anterior, posterior, dorsal, and ventral. And just like many of you know, in the visual system, there's these so-called parallel pathways. We believe that there's an analogous set of parallel pathways in the auditory system, so that there's a ventral pathway that starts in the primary auditory cortex, Gesundheit, that goes up to the prefrontal cortex, and this is involved in auditory perception and decision-making. And then there's a dorsal pathway that maybe sound localization, audiomotor processing, some more temporal sort of processes. So today, though, we're going to be focusing here on the ventral stream. And so what I want to do today is talk to you about two stories. One is a readout mechanism for streaming that was led by Taku Ban-Oh, and then how this is work by Jean-Hugues Lestang. This is work where we looked at sort of population level activity for coding and discriminating between a figure and the background stimuli. So we'll start with, and this is all new and unpublished work. We'll start with Taku's work. So I just showed you a few seconds ago this idea about streaming, right? The idea, once again, is that there's a series of tone bursts. You hear them, and then somehow in your brain, you decide whether you hear two streams or one stream. So I'm going to go back and forth between stream and sound. Effectively, they're the same thing, right? So you either two stimuli or one stimuli, two streams or one stream, right? And so the question that that Taku wants to understand is what parts of the brain are involved in determining whether you hear one stream or two stream. So I guess a long time ago, Michel, who worked with Joseph Roschecker, were trying to make an argument that if you looked at, let's say you had a stimulus that's tuned, that one of these frequencies was say 1,000 hertz, right? And then you presented the other stimulus was say 1,500 hertz. And if you looked at that neuron, what you could tell is that depending on the relative amount that the neuron responds to the 1,000 hertz and the 1,500 hertz stimulus or the 1,200 hertz stimulus, that what you could begin to do is decide by looking at that, you could tell whether it's one stream or two streams, right? And so what they argued is that if you look at the amount of relative response, and over time the amount of habituation, is that you could read out whether it's one stream as two streams. I'll show you what that means in a sec. Okay. So, and what we know is that when I showed you an example of how the speed of the stimulus tells you whether it's one stream or two streams, but also you can do the same manipulation with the frequency difference. So if I have two stimuli that are very similar frequencies, because they're similar, you'll hear them as one stream. But then if there's two streams, the frequencies are very different, you'll hear it as two streams. Okay? And so if you look at the amount of habituation that the neuron has to these two frequencies, maybe that you can use that as a decoding mechanism. Right? So that had a lot of, these were two very important papers. So here's essentially the idea, right? So imagine here, you're looking at the amount of activity for a single neuron, and this is to say the neuron's response to, let's say here in red, it's its best frequency, and here's a second frequency. So early on, when you just present the stimuli for the first time, the neuron's going to respond about the same, right? And if there's some sort of threshold, which is a dotted line, you would say that both of these responses are above that threshold, right? As you present the stimulus over time, what's going to happen is you're going to get habituation, right? The neuron's going to adapt to the sound, and the amount of activity decreases. But the amount of activity change is going to be relative, right? So in some cases, when the frequency is larger, you're going to get much more habituation, and there's only going to be one value that's above this threshold. So you're going to say that's two streams, but in some cases, the frequency is going to be about the same, and you're going to say that there's one stream. So if you have some mechanism for reading out how the neurons respond to the two stimuli, you can use that as a readout mechanism. Okay, good? Okay, so what was the problem with the Michel data and the Roschecker data? So the first problem or concern is that this data was collected with passively listening monkeys, right? So we don't know their behavior, how they responded. And then what they did was they fit the neural data to human behavior, right? So what they did was this model fit of, here's my neural data, and let me fit it to this human data to see if you can get this model to work, okay? So both of those, are, it's reasonable, but we actually don't know in a real monkey when they're actually doing the behavior, does this mechanism work? Okay, so today what we want to do is directly compare neural data and behavioral data. So for those of you who follow streaming literature, this is one of the really, really hard tasks to do because essentially you're asking the monkeys to make a subjective report, right? Do I hear one thing or two things, right? And the stimuli are really subtle. So this has been a very, very hard thing to do. And so what we wanted to do was come up with a way where we could objectively know whether there's one stream or two streams. And the way we did is we came up with a new task in which the monkeys are not telling us whether there's one stream or two streams, but just reporting to us whether they hear a deviant stimulus. And the idea here is that you hear the deviant stimulus only when there's two streams. And I'll explain that in a second. So we tried to get around this objective report, which makes it very complicated to really interpret what a monkey is doing, to going to more of a objective report. Okay, so here is the task. So on the x-axis is time and the y-axis is frequency. So essentially what's going on is that we present a series of tone bursts. So there's a low frequency, then two high frequencies, a low frequency, then two high frequencies, right? And the color scale here is the relative loudness of the stimuli, okay? So for the low frequencies, they're all about the same stimulus. Excuse me, for the low frequency, they're all the same loudness except for one value, which is louder than the others. For the high frequencies stimuli, they're all different sound levels, okay? So the idea is, so if you imagine now these are exactly the same frequency, you wouldn't be able to ever know that this is deviantly loud because it's mixed with all these other stimuli that are both softer and louder, right? So if this is my variability in loudness, and here's the thing that I have to detect, if it's sitting here in the middle, I'm never gonna be able to know that that's loud, right? So you should never be able to hear this as a different stimulus, okay? If I increase the frequency difference, and I know that when I increase the frequency difference, perceptually, I should hear those as two different stimuli. So now, if I'm playing a series of low frequency stimuli that are all the same loudness, then one is louder, I should be able to hear that. Because now I'm hearing two different things, and I should be able to hear something that instead of it being like this, it's like this. Right now, this is deviantly louder. Okay, so now the monkeys aren't telling me if I hear one stream or two streams, they're just telling me whether they hear this target, and we're using that as a proxy for whether there's one stream or two streams.
How much is it natural for monkeys and how much is just training?
So streaming is streaming phenomena is universal across the mammalian species, right? So I mean, it's just a part of how all mammal brains work, right? So the hard part though, is training them to to tell us, okay, pay attention to this stimulus here and report that, right? So that's the hard part is trying to communicate to them, tell us when you hear this and report it, right? So the underlying mechanisms we think aren't trained in, what we're training them to do is pay attention to this particular frequency band and then tell me when you hear this, right? Just as if, right, and so actually, when you look at sort of, if you look at sort of how well animals can distinguish between different phonemes, right? All animals can distinguish between, like phonemes like ba and da, just the same way we can, right? So language was built up on sort of these fundamental processes that exist across all animals, and we added some complexities with grammar, but the basic sort of our ability to perceive different types of phonemes is universal, right? Once we got language, we got more complicated about, when you learn language and not learn language, but the basic acoustics are the same, right? So and as humans, we just added a little bit fancy things to it. Okay, everyone good with the task? Okay. So, I may describe this sort of low, high, high combination as a triplet, okay? And so how the monkey's doing the task, how they're reporting it. Essentially, we have a monkey, they're holding a joystick, and when they hear the target stimulus, they just move the joystick to get a reward. So pretty straightforward. So here's some data from a particular monkey. So here we're looking at the delta F, so the frequency separation between the low and the high frequency. So here it's small and there it's large. We're showing you this in terms of D prime. So this shows hits, a relation between hits and false alarms. And the important thing to note is that as you go from small frequency differences to large frequency differences, the monkey gets better, implying that the monkey's more readily able to hear the target and that there's more streaming going on. Granted, for those of you who know D prime, these are not the largest D prime values you'd ever want to see in your life. These are, streaming tasks are ridiculously hard to train. I'm never doing it again. I'm retired from streaming. No more streaming. Okay, so we got the behavior. Okay, so now how does this correlate with neural activity? Okay, so when I'm going to be showing you data, most of the data I'm going to be showing you here is in terms of triplet position, so those low, high tone bursts. So when I say first, that's the first one we present, first triplet, second triplet, third triplet, and T-1 here means it's the triplet before the target turns on, okay? And I'm color coding here. Red is the data from the smallest frequency difference, delta F, and the blue is the largest. And on the y-axis here is the area under the ROC curve. So you have two distributions of data, right? And you can come up with a metric when the distributions are exactly the same, it's 0.5. And as the distributions become more and more different, you get closer to 1, okay? So 0.5 means they're exactly the same. 1 means they're entirely non-overlapping, okay? And so what you could see here is that when you look at this relationship, you see that over time, neural activity habituates. Nothing surprising. If I present the same stimulus over and over again, the brain habituates to the repeats of those stimuli, right? That's because what the brain cares about, it cares about change. So if I present the same thing, it's not important anymore. I only care about things that change. So this is not surprising and consistent with what everyone would expect to see if you're recording these sorts of tasks, right? And at the end, there's some difference in the amount of habituation you see, but the important take home is that you get this habituation. Okay, so now what we did was we created an ideal observer model where we just asked the question of how much of this habituation is there for the low frequency responses and for the high frequency responses, and we just decoded that, right? And so here it's we're plotting this again in terms of time, and what we're doing here is the output of that decoder. And the probability of that decoder saying 1 stream or 2 streams, right? And we're going again from the smallest delta F to the largest delta F. And what you can see is that when you're at the smallest delta F, so the two frequencies are overlapping more or less, you hardly ever will say that there's 1 stream. But as the frequency differences get bigger, you more often than not are going to say 2 streams, okay? So this is, to this point, this is what Rorschach showed in 2005, is that, yeah.
Where are you recording?
Oh, sorry, this is primary auditory cortex. Sorry, very important point. So as far as this is entirely consistent with what Rorschach showed, is that as the delta F gets bigger, you're going to have more habituation, and you should be able to say 2 streams more often than not, okay? But what we don't have is the behavior. Right? So I'm showing you now, this is the graph I just showed you. Now here what I'm doing is I'm separating the data out in terms of whether or not the monkey heard it or didn't hear it. Okay, so hits versus misses. So what you could see here is that the solid and the dotted lines are perfectly overlapping. So this cannot be any sort of mechanism, at least in our mind, for a perceptual decision, because this mechanism is totally invariant to any sort of choice. So this is just, in our head, this is just sort of a byproduct of of just neural habituation, right? But it doesn't actually reflect what the monkey's choices are. However, we do see, it isn't just like there's no perceptual information here, right? So what I've gone back to here is this is another one of these metrics of neural activity, so this ROC, and now what I'm doing is I'm plotting it as a function of D prime. And so this is what we do is you break apart the triplet for the low frequency, then the two high frequency parts of the triplet. And as you could see is that within it, so this is like session data. So in sessions in which the monkey did really well, so there's a larger D prime between how they did on the small and the large. The neural activity there's more, the neural activity is different than when the monkeys did poor. And you can see this better for the high frequencies and low frequencies. So the neural activity is modulated by the monkey's behavior, or the behavior is modulated by the monkey's responses. You can argue the causality of that. However, it doesn't, this readout has nothing to do with actual the monkey's choices. So going back to this figure that I show you in a second, is that now I have that same figure, but now I have, the dotted line now is misses and the solid line is hits. And what you can see here is, and the take-home message is that it's exactly the same. And so this really can't reflect any sort of perceptual information. You get the habituation, you clearly, it's different whether it's one stream or two streams, but it's not really a decoding mechanism per se. So somewhere downstream, you have to, there has to be a mechanism that's sensitive to the differences and not just this readout. Okay, so let me pause there for questions, anger, violence, perhaps. Good.
So basically, it's only replicating.
It's just, yeah. So this right. It's just this is neurons have tuning properties, and if I play stimuli with different frequency properties, they're going to have differentially be modulated by them just due to, you know, sort of feed forward synaptic activity. And it just so happens that, you know, it turns out that like if it's high frequency or whatever it is, you get this differential habituation. And that just happens to map on to sort of perceptual reports. But you can't like decode that as but it has nothing to do with choice, right? That's why it works, you know, that's why lines of behavior, it doesn't matter what you're doing, right? It's sort of like, you know, like when you look at mismatch negativity, right? These are sort of feed forward processes. They have nothing to do with behavior. They're just sort of how synapses work, independent of any more cognitive thing.
So I'm not an expert on, you know, I've been educated by people here in science research. When you refer to having a neuron that replicates these frequencies and I assume that what you're referring is the processing of some registers that you got from a bunch of neurons, and then you transform that information into something that you call a neuron. Am I right?
So you're recording neural activity. So recording neural activity, record it as a function of the frequency difference between the stimuli, and also as a function of whether the monkey got it right or not right. Right.
And it's not that you are actually registering a single neuron.
No, we're recording from single neurons.
You are registering.
Yeah. Single neurons. Yeah. Yeah.
And so that means fantastic, because it's hard for me to imagine that when you hear something, there would be only one neuron.
Well, there's not just, we're recording one at a time. The number of neurons you need to sort of modulate your perception is more than one, but it's actually, you know, people have estimated, like I think Nikos Logothetis, who's in China now, but he was in Germany in Baylor University. He estimated, others have estimated hundreds. If you could tickle a couple hundred neurons, you can change your perception. So if you could artificially modulate the activity of a few hundred neurons, I could change what you see or what you hear. Perhaps one neuron won't do it, but you don't need, it's not thousands, it's not millions. A couple hundred, given the right task and the right parameter set. Yeah.
And the right area.
And the right area. Right, yeah.
I was trying to follow what you, the area under the ROC.
Yeah.
The two distributions that you're using to compute the ROC, what are they? So it's like the neuron response.
That's to the low, it's the, well, it depends on when it is, right? So it's over time. So the ROC is just the first one I showed you was just how the neuron is relative to to so a baseline condition, how it's responding over time. So how much habituation you see over time, right? It's earlier on in the trial. Okay, so we have it, and then we're comparing over time how much habituation you see over time, right? And then with the decoder, it's we're just comparing to asking, what's the relative response, and we establish a threshold. We establish a threshold, and we ask, is the neural activity above that distribution or below that distribution, that threshold?
I think I'm just trying to digest what you have
Right.
on the previous slide, but you have to further.
Right. So so here it is. Right. So okay. So this is all sort of session dates. It's essentially session by session. The y-axis, x-axis is session data. So like that's the behavior, right? And then the ROC here is how much is, once again, is for the low frequency tone burst, and say so early on in the trial versus later in the trial, we just compare those two distributions, right? So to say, how much does it habituate, right? So we're just here. It's just two time points, early and late, and we're just looking at those values over time. And the point is that when the monkey's doing really well, we see more habituation than when they aren't doing well, right? Because the habituation is important for the streaming, but it's just not that at the level of primary auditory cortex is that is modulated by the choice. But there is clearly some choice-related activity here, perceptual-related activity here, because if not, all those lines would be essentially flat, right? Is that clear up?
Yes.
Okay. Yeah.
Out of curiosity, when you're listening to difficult performance, there's always a melody and there's always the companion.
Right.
Consider the screen and what's the difference in frequency you need to have between the screens to repeat that.
Right. So the question was, how much when you hear a concert, there's a melody, and how much do you is it? So it gets in real world, right? It gets very complicated, right? Because it's timing information and it's frequency information and it's how closely information follows one from the other, so how much you can track it and follow it, right? And so there's cultures where there's essentially three different people playing a xylophone. If you listen to each of them independently, it all sounds like random. It's fine music, but there's nothing really to it, right? But when you hear them together, all of a sudden emerges these multiple melodies that you can distinguish. But from each xylophone, you can't. There's no way you'd ever, right? Like Mozart, also he knew this. He didn't know the words, but he could have different instruments playing, and in the composite, you'd hear these melodies and these patterns that you would never be able to assess by hearing a single person play, right? So that so this is like, how did Beethoven compose music when he was deaf, right? It's because he had the intuition to understand like how these things work together, right? He didn't actually have to hear it. They all have these composers have this intuition. So it depends on the music, but it doesn't mean you could have these streams, these melodies go across multiple different instruments that, and it doesn't have to be all violins, right? It could be violins to some wind instrument, right? But as long as they're sort of having this continuity and playing within the same key, you can follow it across. And so it's really remarkable. Like, we all sort of know this in our heads, right? But we just, and composers can figure it out. Yeah.
Maybe I didn't know if it would be makes any sense, this question, but you have the control of the hearing threshold of the monkey. If they have the similar hearing threshold.
Yeah. So these are all. So monkeys actually hear a little better than we do on average, and these are all super threshold. So, you know, so it's not an issue of like very soft sounds. These are all very, very loud sounds. Not very loud. So it's not like you can't hear them. We're not asking them to detect. We're not asking them to detect like very, very soft to something that's just soft, right? It's sort of loud to louder.
You go to the second
Right.
part. Then if neurons in one are not decoding the signals,
Right.
where they are.
So, right. So in our hands, in our studies, which doesn't mean it's true in other people's hands, in other people's studies, we see a lot of decoding in areas like that A1 feeds to, which is called these belt regions. So we've seen we can so we can do manipulations in this it's called the anterolateral belt, where we can do manipulations where we can actually see, we can affect the monkey's perception, and we can see that the neural activity is very much modulated by that. So the next thing to do, if I go back to streaming, is we need to record sort of these other areas to see where it is. Okay, good. Oh, one more. Right.
My question is more related to the integration and auditory information according to the mechanisms of memory. Is there any relationship between hearing disorders, for example, and the presence of altered neurotransmission in hypothalamus?
Yes. So that's a huge area. So there's, yeah, so people are beginning to believe that, for example, that hearing loss causally relates to dementia, right? So people used to think that, so if you have hearing loss, right? So let's say you have a relative with hearing loss, right? And they don't have a hearing aid, right? So they would stop coming to family events because they can't hear anything, right? And so they would stay home, and that sort of that lack of social interactions would then cause the dementia because they just weren't activating their brain, right? But now there's lots of evidence, and I would direct you to a review paper by Tim Griffiths called The Hearing Hippocampus, where there's he argues for causal evidence that we don't know why, but that actual hearing loss will actually cause changes in hippocampus and medial temporal areas that then causes dementia, right? But the mechanisms are really unknown. But people are beginning to really, as in general, as our population ages, right, we need to sort of think about how to preserve mental capacity, and should we just give everyone a hearing aid when they turn 50, and that'll solve the problem, right? But this is a very important sort of new field. Okay, so we're going? Okay, so let me introduce the stimulus first, and it's sort of this idea of sort of repeated stimuli can allow you to hear do the segregation. So imagine, and this is a stimulus that Tim Griffiths generated with folks, with other colleagues, Chris Petkoff, that we essentially stole. So here is time, here is frequency. So imagine what I do is I create a stimulus that just has random frequencies that occur over time. So there's nothing regular about this pattern, right? I just have turning on and off stimuli, right? So you'll hear this as effectively as noise, right? Just random stimuli. But if at some point I now play, let's say, these red stimuli at the same time, and then I repeat them, what's going to happen is that as I repeat those stimuli more and more, or there's more and more frequencies, all of a sudden that emerges as a figure. You hear that segregating from the background. Okay? So having stimuli that occur at the same time and that repeat is a way to segregate stimuli and create sort of a figure versus the background. Okay? So the question we want to ask today is essentially how is this encoded in the brain, and in particular we want to understand is how is the network properties of the brain important, meaning I'm looking at a lot of neurons simultaneously, and I assume that because they're connected to one another, that network is important for this phenomena, or is it just some sort of simple thing about, oh, I'm playing a sound and the neuron is activated and it doesn't matter. So we want to begin to understand sort of how the network responds and what's the relationship between the frequency tuning of the neuron and how these neurons respond. Okay. So here what we do is we're in primary auditory cortex. We're recording. We have a multi-channel electrode, and we're recording simultaneously different electrodes. So now we're thinking more about population activity in primary auditory cortex. And so what we're going to do is we're going to record these neurons. We're going to identify their tuning properties, and then we're going to tailor the stimulus to the tuning properties of these neurons. And then sometimes the tuning of the stimulus will reflect the background, and sometimes it'll reflect the figure. I'll show you what I mean in a second. Okay. So here are examples of 4 stimuli. So these are spectrograms. So you have time on the x-axis, frequency on the y-axis, and essentially the yellow colors are the stimuli that we're playing, right? So here, and the red line is always sort of the average tuning best frequency of where we're recording. So in some case, and the white line here demarcates when we go from the just ground to figure plus ground, right? So if we go back, so once again, the ground is when we just play stimuli in random ways, and then when we say figure plus ground, we still have the stimuli playing randomly, but then all of a sudden we superimpose a number of stimuli that always occur at the same time and repeat. Okay. And for those of you who are aficionados, the number of frequencies that we always play is the same, so the overall loudness is the same. So that's our control. Okay. So the red line here is the best frequency, and here's the situation when the ground stimulus is at the site's best frequency, but also the figure is at the site's best frequency. Here's an example where the ground is also at the best frequency, but the figure is outside of that, so outside of where the neuron responds. Okay, and here's 2 more examples. So here, the ground does not encompass the neuron's best frequency, but here the figure does. And then the last situation here is that both the figure and the ground do not encompass the best frequency, right? So we have the tuning properties of the neurons, we have a figure and a ground, and so we have the 2 by 2. Are you in the within the tuning properties, outside the tuning properties? Is it figure or is it ground? So we have the 2 by 2 matrix. Okay. So and essentially, we present these stimuli, and essentially the monkey is going to respond nominally when they hear this figure.
But when they find the tuning properties of that neuron,
the population.
The whole population.
Yeah.
And restraining that frequency band, or it depends on the amplitude of the stimulus. Like it can like enhance other frequencies, like the response of that neuron for other frequencies. You know, like the B tuning.
Oh yeah. So right. So right. So we didn't really go into the whole is it all relative? We just said here's the best frequency, and we're presenting everything at the same sound level, right? So obviously, given a set of frequencies, it's going to drive it more or less than the others, right? So that's an important point. We didn't really play with that because then it just becomes too hard, right? Okay. All right. So here is this is to show you sort of the tuning properties of a neuron. This is called a spectral-temporal receptive field. We have time on the x-axis, frequency in the y-axis, and color here represents the probability that the neuron fires. You get X potentials, and so here this neuron has a high probability of firing, about maybe 18 to 20 milliseconds after you present the stimulus, when there's about a 2 to 3 kilohertz stimulus, right? So this is a nicely tuned neuron. Okay, so we see that the neuron is tuned to about 2 to 3 kilohertz. So now we tailor our stimulus to be, the figure in the ground to be related to that. Okay. So here what I'm doing is I'm showing you in the same order that I showed you the 4 stimuli, how this particular neuron responds, right? So 0 here is when the stimulus turns on, and sorry, it disappeared. But 0.5, excuse me, point right here is when the ground turns on, right? So you can see here really nicely. All of a sudden, the neuron is sort of hardly responding, and then it begins to respond more when you turn on the figure. Okay, so the neuron responds in a very characteristic way to each of these stimuli. No big deal. Okay, you can now do the same thing. That's now the population from that session, and once again, you see that the population looks like that neuron. Okay, neurons are tuned to the same frequencies. If you look at one neuron, you look at 20 or 30 other neurons together, you average together, you get pretty much the same thing, right? Not a big deal. What you can also do is do something fancy where you can ask how well can you discriminate between the 4 stimuli, right? So here, what you can do some dimension reduction because you have 20 neurons in a stimuli, and each of the colors here represents the 4 different stimuli, and you can imagine you could put a line here, or here, and here, and fairly accurately tell me what the stimuli are, right? So my question to you, is this interesting, right? Neurons have tuning properties. I'm manipulating the tuning of the stimuli. So when, of course, some neurons respond well, when in the stimulus, when the tuning properties of the stimulus match the tuning properties of the neuron, and it's respond poorly when it doesn't respond, right? So not a big deal, right? Neurons tuned to 1,000 hertz. I play 1,000 hertz, you get a lot of response. If I play it, say, 1,000,000 hertz, I don't get a response. So I do some fancy, dimension reduction. I can show you that they're different, right? Who cares? But the question then is this just due essentially to the individual neurons firing, right? These individual tuning responses, or is it related to how these neurons are hooked up as a network, right? So to get at this question as a first approximation, I can't, the neurons are hooked together. I can't pull out a single neuron and look at it by itself, right? Without the rest of the monkey, right? And I can't sort of decouple one neuron from the other neurons. But what I can do is I can model that each neuron's sort of base low-level responses, their linear properties, and then see what you get, right? So we're doing this with these sort of, it's called a linear nonlinear model, where essentially what you do is you take the stimuli that you use, you essentially convolve it with the STRF, the spectral-temporeceptive field. So this gives you the linear response properties of the neuron. And then what you add in is you add in this sort of this exponential output to it. You pass it through. X is your stimulus, and this is the probability of giving a spike. And then you can generate spike trains. So this is the nonlinear part of it. So this is a very sort of general flavored model, right? So what I do is I record in a session. I get 20 neurons. I generate their STRFs, right? And then I model each neuron. And I'm going to assume that that's my population of independent neurons, because I've taken out how they're talking to each other, and I've taken out all those like ugly nonlinearities, okay? So here's from the data I showed you a few minutes ago. So once again, in the order of the stimuli, you have time, and now I have some z-scored spike rate, and the color is the actual response of the neuron, and the gray is the modeled response, right? I don't know, and depending if you're half empty, half full type of person, you might say it's good or you might say it's bad. Okay, and we can, it's what it is. So that's for one simulated neuron. I can also do it now for the population, and this looks fairly reasonable. I don't know, there's a little bit of a difference there. But once again, It's, this is like, linear modeling 101, so not doing anything fancy, and it looks pretty good, more or less. So now you go back to the dimensionality reduction. So here is the data I showed you before. This is with the real neuron, right? And you could see this clear differentiation between the 4 stimuli and the 4 colors. Now this is what you get when you're doing it with the model neurons, right? It's just a circle, a mess. Maybe it's some sort of nice painting at a modern art museum, right? But clearly there's here there's separability, and here there's non-separability. And you could also ask the question, you can put this through a classifier, put the neural responses through a classifier and ask how well can you discriminate with the real data. Chance here is 25%. With the real data, you're doing pretty well. With these predicted, you're a chance. Okay? So that suggests that these network properties are important, but are these network properties hardwired in, or can you modulate them? So
Do you infer like circuit because of the model, the similarity with the model, even when the model is actually built on the shape of the response, of the probably response of the neurons? I mean, wouldn't that be a consequence of the shape of the model rather? You know what I mean?
So
probably you find like a correlation with the model and the neural response.
Right, you can find a correlation. Right. So So obviously the model is going to pick up some property of the network, right? But the idea is that the model response is just picking up, let's say, essentially the linear response to it. And so, if that's all that matters, that's what the neuron is tuned to, that it shouldn't make a difference. But clearly, when you have the actual neurons are doing it. You're right. It's a proxy for this idea of how can you pull apart all their connections, between them and sort of get at it, right? But are these? Yeah.
Sorry, just on that point, like, what were the stimuli you used to measure this here? Were they the stimuli themselves? Like,
no, so that's it was these random chords. Yeah. So it's these random noise that go right. So a totally different stimulus set.
Yeah. But if you were to measure that here based on the stimulus that they're given, you would get better models.
Well, maybe, but you couldn't use those types of stimuli. Those would be really poor stimuli to generate an STRF. Right? They don't have the right properties.
So
what? Yeah, but they're very sparse tone clouds, right? Right. And so I also think it's yeah, and I think I think these are actually I mean, one could argue you should use the same stimuli to generate it, but I think this is a rich it's a richer stimulus to use to actually generate it out. And there's been lots of folks who've done work, like Monty Scabi's done work to say, if you have similar, types of whether it's a tone cloud or these, these dynamic ripples, essentially you get this, there's jitter around the edges, but essentially, there's no real difference in how you get it because it's really just that linear, linear component, right? And more importantly, what's fascinating is whole different side note is that you only get STRFs in like very small population of neurons in auditory cortex, right? It's only like 20 to 30% that you can generate a STRF because the linearities are just because neurons aren't just phase locked enough, which is very different that if you try to do an STRF in primary visual cortex, 100% of the neurons you can generate something. So once again, when people say auditory and visual cortex, just cut paste. Why do we need to study the auditory cortex? We have all the vision people. Is that they're totally different beasts, even at very low levels. Okay, so the question is, we think that these network properties, we think they're important, but are they hardwired? So a really simple, silly thing to do is that you, at the end of the day, when the monkey is done working, you just remove the joystick from them and present the stimuli and have them listen, right? So now it's the same stimulus, the same neurons, but now the monkey's in a different state. We can call it active versus passive. We can call it whatever you want, but two different states because one, he's engaged in the task and the other, he's not engaged in the task. And what we can do then is we can just, we can measure sort of what's called the noise correlations. So how well on a trial by trial basis does the neurons sort of fire together, right? So what you see is that in the passive situation, the noise correlations are much higher than the active in the active state. So whatever these network properties are, they're modulated by behavioral state. And also you can break it apart. Maybe it's, neurons should fire together maybe when they have similar tuning properties. So you can break this apart. So neurons that are similarly tuned also have this pattern of higher noise correlations than in passive and active. And then if you look at neurons that have very dissimilar tuning, so maybe they shouldn't be talking to one another at all, it also has the same sort of phenomena, maybe a little less exaggerated. So, so the summary from this is that figures ground segregation via sort of temporal and spectral coherence is mediated in part, by some network properties, and these network properties are modulated by behavioral state. And so the overall summary is that at least in early auditory fields is that neural habituation exists, but it really doesn't appear to reflect the monkey's behavior, its choices. And there needs to be some sort of downstream area that's involved in that. And then and that figure ground segregation appears to be mediated by network properties of the auditory cortex and is not simply due to sort of independent tuning properties. So with that, I'll leave you. So as I said, Taku did the first part of the study and Jason Lee helped with some of the early recordings, and Jean led the second study. A lot of this work was done in collaboration with my colleague Vijay Basmaranian and early work with my good friend Josh Gold. And here is some of our funding partners. So thank you.
I wonder if by the expression, I am assuming that at the beginning the animal is more engaged in getting the reward, and later no. Would you see the difference in the correlation?
Yeah, that's a good. We haven't looked at that. It's a good question. And yeah. So we can easily track that, or you could easily, early versus late, or you could sort of break it apart as a function of, sort of short term, like percent correct, right? Maybe over whatever 30 trials they're 100%. Maybe in the next 30 they're at 50% or whatever, right? Does it change there? So you could do lots of ways. But yeah, it's a good question.
I have just a question about like where in A1, like the core.
Yeah, well, A1. So primary. Yeah.
A very basic question. Is facilitation, the facilitation that you report from the primary cortex produced in the cortex, or then the primary outcome?
So what the
facilitation?
From.
You report that there is some facilitation, but.
You mean the first study? Yeah. Oh, so that's a good question. So no one has looked at streaming in the midbrain. Our assumption is that my assumption would be is that you see some of it you would see in the thalamus, but not much earlier. So if you do what's called oddball tasks, where I present beep 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 boop beep 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 boop, and so it's a different task, but people it's this idea once again you hear the boop is different, and the brain responds very much to that, and people do these oddball tasks when you're in surgery and having brain surgery. They present these stimuli to you as an index of brain health, right? So the anesthesiologist is working with other folks. So it's actually unless you're really in a really deep coma, you get these responses. And people like Jennifer Linden have looked to see where that difference in responsivity to that boop, the beep 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 boop, and she sees it in thalamus, but doesn't see it in earlier, like inferior colicus, earlier areas. So suggesting that at least part of it, at least for these oddball, originate in thalamus and then maybe are further enhanced in cortex. For streaming, no one has looked earlier than cortex. Maybe in birds, but I don't think so. Great. Thank you very much.